Hello. Yes, it is. Thank you very much. All right. Hello, everyone, to the second talk of the introductions. My name is Iva. I am currently a postdoc in Paris at Paris Observatory in collaboration with Leiden University in the Netherlands. And I just wanted to mention, because we're here from a lot of different places, I'm also from some very small countries. I'm originally from Croatia. I grew up in Austria. I did my undergraduate degree at University of Vienna. I moved on to the Netherlands to do my master's degree at Leiden University, then moved to the US. I was at Space Telescope Science Institute for a while, started my PhD there, then moved back to France. Between Honora and the Laboratory for Astrophysics in Marseille, I finished my PhD. Then I moved to Paris. So just to give a bit of context that like all the past that we see from people, like obviously all the people way above me, but also on our level, they go very different ways. So just to encourage everyone to totally go their own way and like engage wherever you can. The scope of my presentation today is a very, very broad one. I want to take you through the fundamental principle of optics, the principles that we use to describe light in the optical and near to mid-infrared regime of the electromagnetic spectrum. This will obviously miss a lot of the very, very important details that we use in our day-to-day work. So I really want to highlight that I based my slides, my presentation very much on one particular book that is Joseph Goodman's Introduction to Fourier optics. There's a lot of really good literature on the topic. This is usually cited as the reference book for what we're doing here. So I encourage everyone to really go out and look up even more because I have 40 minutes. I will make the best out of it. And obviously, let's continue the discussion during the week about all of that. So what is light and how do we describe it? First of all, why are we interested in this at all? The thing is that when we work with optical instruments, when we work with high contrast imaging instruments, what we're fundamentally looking at is how does light propagate? So in order to understand what's happening, we need to find a way of describing it. Once we understand it, once we want to describe it, we can actually start manipulating it. So we can build instruments not only to measure light, but also to impose changes to this light, for this light to do something that helps us to do our detections. And in between, there's this area of numerical manipulation, of numerical simulation, where if we understand what is happening physically, we can translate that into the world of simulations in order to prepare our instruments and model what is going to happen. So usually what we're going to look at and what we want to understand is how does light go from one point A in space to one point B in space, and what happens to it in the meantime. Now, light has been the topic of research for at least 3 centuries now. There's been a lot of different researchers looking at it. One of the people who's been very interested in it and very active was Isaac Newton. There's a lot of things he got right. There's a lot of things he got wrong about it. But in the meantime, over all of these years, we have moved into an era where light fundamentally is used for almost all of the day-to-day applications we use in our lives. The most obvious one is one that we use almost every day, depending on how you live your lives, is literally to take an image. Take an image, capture the photons that depict an image, then either post it online or put it in your slides. And this is also the application that we use when we do direct imaging. So more concretely, the application, and this is what Beth already introduced, is we're going to look at how does light propagate through and how do we measure light inside a high contrast imaging instrument. So we will be looking specifically at these things today. Now, when I talk about optics, optics is a huge field, and there are many different ways of looking at it. What you might have gone through in some of your courses before is the framework of geometric optics. So in geometric optics, we assume that light propagates on straight lines, on rays, and different optical elements make those rays converge, diverge, and eventually we can model the images that we get in spot diagrams. So what I'm showing here to the left is a ray diagram image, a geometric model of the James Webb Space Telescope, and in the middle, a sort of fake spot diagram of a very, very optimal optical system where all of your rays converge in your focal plane and give you one spot. The thing is that this is not entirely true. And this becomes immediately evident if we actually look at an image of the James Webb Space Telescope. And we see that when we get close to the diffraction limit, which is also something that Beth already alluded to, geometric optics is not sufficient to explain the images that we see with our instrument. So what I'm getting at here is that fundamentally, light does not necessarily behave like a straight line. It behaves like a wave. Now, light also behaves like a particle, and this dual nature of light is a very interesting phenomenon in and of itself. But when we talk about Fourier optics, we're interested in the properties that light exhibits when we think of it as a wave. So ever since about the 18th century, we know, physically speaking, that light is a transverse electromagnetic wave. And what this means is that we can explain its behavior through Maxwell's equations. And Maxwell's equations say that electromagnetic waves have an electric field component and they have a magnetic field component. And both of these components are described by a full vector at each point in space. So this is a vector model, a vector theory of describing electromagnetic waves. It turns out that in most high contrast imaging instruments, in astronomical instruments, that there are certain conditions that apply, which allows us to model light as a scalar field. So now what we can do is we take one single point at each position in space. So we take the proxy of the electric field, a scalar electric field, in order to describe our light. And this is what I mean down here with this very first equation I'm going to show, is where the electric field of the light is just one number per position in your space. Here's an R vector. You can make it X, Y, Z. It really just depends on how you define your coordinates. Okay, so there are different ways how you can describe your light. One of the very useful ways to describe light as an electromagnetic, an E-field at this point, so we've reduced it to the scalar theory, is to look at its components in terms of amplitude and phase. So A is my amplitude, phi is my phase. Also note that an E-field, an electric field, a wavefront, a wave field, all of these I'm going to be using synonymously during the entirety of my talk. They all mean the same thing in this context. What does this mean when we talk about wavefronts propagating through space? I'm trying to show this with this image. So when we have a light source, when we have a point source, an unresolved point source very far away, what happens is that this point source is emitting light in terms of spherical waves. Now, in general, in astronomy, those point sources are so far away that these spherical waves just keep expanding. And since they're so far away, by the time they reach us, we will be looking at such a small part of the surface of these spherical waves that we get something that is a plane wavefront. I'm showing exactly the same thing again on this slide with just simplified figures, because those will be with us for the rest of this talk. So we have a point source with a diverging wavefront of spherical waves. If that propagates a long distance, this actually turns into a plane wavefront that I show in the middle. I think I might have to be pointing here. Yeah, a plane wavefront in the middle. One important part about this is that we consider plane wavefronts a special case of waves in which there is a plane that propagates perpendicularly to its direction of propagation. So what this means that we have a constant wavefront propagating. You can imagine this as usually what people do is like, you have a wavefront, a constant wavefront that just propagates perpendicularly to its plane, right? Now, I keep saying a constant wavefront, that this does not mean uniform wavefront, right? So I can actually introduce some aberrations into this wavefront. It's all scrambled up. We'll talk about aberrations a little bit later, but this is now a non-uniform wavefront, might have a non-uniform phase, and yet it travels as a constant wavefront. And when I say constant, I mean constant to some reference phase, any reference phase. So when we talk about constant plane waves, constant wavefronts, this is what we mean. They travel as a constant wavefront along the z-axis. And right, one thing also is that I've written it in this way here, because I wanted to make clear that once we can describe light as a plane wave, what we're looking at in each wavefront is just a function of position in this plane, in this plane wave. Okay, so now that we've established what the wavefront is, this is how we want to be looking at light. How do we actually describe the propagation analytically? I will be jumping through a couple of equations here that I will not be describing. So please, come talk to me, come talk to the other experts in the room, go through the literature. But in general, we can describe the propagation of light with this equation where we can derive the electric field as a function of an arbitrary position in space in terms of spherical waves. Now, I said that we're actually interested in plane waves, so we can actually use the Huygens-Fresnel principle in order to decompose any plane wave into a sum of wavelets. So this is what I'm showing here on the right. So what we can do is, as this wavefront is propagating, any further point in space, we have a different plane wave that is actually composed of a sum of these wavelengths. So what we have here is an equation is if we have an electric field in point 0, now we can calculate an electric field in a different point in space at a distance that is described by the vector s by this equation. So this is great. This is an analytical expression, but it is really hard to compute. It's possible, but if you can, you want to reduce this further. And this is the point where we start making approximations about the propagation in order to get something that is easier to compute. So what we usually do is we take this vector s and we apply some assumptions and approximations. In the first step, what usually happens, we go to what is called the Fresnel regime. Since we will be looking at far field imaging, though, I will go even a step further and make my constraints and approximations even harder, and I will jump straight into the Fraunhofer regime. So the Fraunhofer integral applies a lot of these, or the approximations on the distance between the 2 points, between the 2 planes that we want to calculate. And then it looks literally like this. So here you have an electric field as a function of the coordinates in its plane. And they are calculated with this integral. The approximations that we do here have an assumption that the observer, or the plane in which we're calculating the electric field, is very far away from the object that we're looking at, from our aperture. So the way you can imagine is if I have an aperture on this side of the room, it's very small. The further away I go, at one point when I look back, the aperture would look as if it is on axis. It is very, very small. What also becomes obvious from this is that it's not the absolute distance z that matters in order to put us into this far field regime, but it is the ratio of the size of the aperture to the distance. And when we look at the ratio of the size and the distance, we're looking at angles. And this is what should make it intuitively understand that when we go into the far field regime, into the Fraunhofer regime, what we care about are the angles in our aperture. And we will come back to this also during the talk. So this is now an integral that looks much simpler, and it is actually really simple because it is in essence a Fourier transform. What I'm showing here on the second line is the expression of a 2-dimensional Fourier transform. So 2-dimensional because we're looking at a plane with an x and y coordinate, and the function to transform in this case is simply our input electric field. And this is extremely handy now because we can go back into our drawer to the very well-established framework, the mathematical framework of Fourier theory, of Fourier transformations, of the properties of the Fourier transformations to describe the physical properties of the light. And a shorter way to write this is something like this. There's many different ways to write this. I just chose this because I thought it would come in handy for this talk. I usually also do this for my papers. But what we're saying here is that if I have an input electric field, as I propagate through my optical system from plane to plane, this is also something we will come back to a little bit later. If I Fourier transform this, I get to the wavefront in my next plane. Okay. So I said in the beginning that the thing we are interested in is to describe and understand the propagation of light through an optical system. What this usually means is that we have an input wavefront into this optical system. It propagates a certain distance, z, through different planes, and it becomes an output wavefront. The usual way of doing it is that we will be interested in specific states of the light along this propagation. So obviously there is light between the optical planes we define in our optical system. But we will be interested in specific planes because they will have specific properties. Planes are also where we get access to a wavefront. These planes are where we can stick in optical elements to actually act on our wavefront. We can change it. This is oftentimes what we do in chronography, in wavefront sensing and control. You will hear a lot more about this during this week. And one very obvious plane of interest is usually doesn't have to be the final plane in your optical system, but a plane in which you stick in a detector. Sticking in the detector is a very natural way of getting measured access to the information that is the light in your optical system. The thing is that the way physical detectors work is that we are sensitive to the energy of the electric field. We're not sensitive directly to the electric field in this wavelength range of optical and infrared. So what we can measure is not the electric field itself. What we measure is the intensity. And the intensity can be calculated from the electric field. It is its square modulus. This is something, this is a very, very fundamental relationship that is important to keep in mind because this is what we measure. We can describe electric fields, but we measure intensities. Okay, so we have an optical system. We have different optical planes. I can assign names to these optical planes. I can assign name to the wavefronts. Here, I just call them electric field 1, electric field 2, electric field 3. This could be way more planes. It could be less planes. And just to bring the point home about Fourier optics. So in Fourier optics, the specific planes we're looking at are pupil planes and focal planes. And they are Fourier transformations of each other. So if I go from a pupil plane to a focal plane, I do a Fourier transform. If I go from a focal plane to a pupil plane, I do a Fourier transform or an inverse Fourier transform, and there's some scaling of units going on. But fundamentally, those are always Fourier transforms of each other. The next thing I want to show you is a simple example of everything I just talked about. So the simplest optical system we can think of in this context is a simple telescope that has one converging optics, like a lens. It could also be a mirror, but lenses are usually easier to draw because mirrors reflect the other way. And this lens focuses the light onto the focal plane onto a detector. Also here, I drew like this concept again from earlier. Usually we would look at an unresolved point source, a star at infinity. So obviously that light starts as spherical waves, but once it reaches us, once it reaches the telescope, those will be completely plane waves if there are no aberrations, which is also something we will talk about a little bit later. So here we're dealing with exactly two optical planes. One is the pupil plane, the telescope aperture, and one is the focal plane where we have the focused light where we get our image. So what I really like to show at this point is what these electric fields look like. I want to give a little bit of an idea because especially in the hands-on sessions, you will be working with different optical systems. The electric fields will look very differently. So I want to explicitly show them. So I used for both of them the expression I showed earlier, where each of these is composed by an amplitude and a phase in the exponential. Obviously, the amplitude in plane 1 is different from the amplitude in plane 2. This is why they have different indices. So what we want to do here is now let's display the electric field in this pupil plane. Now remember, an electric field in this context is a scalar complex field. So we have one complex number as a function of each xy coordinate in this wavefront. A complex number is a number, but it consists of two parts, the real and imaginary parts. So I somehow have to find a way how to display both. So the simplest way is to just separate them and do exactly that. Take the real part of your electric field and plot it. Take the imaginary part of your electric field and plot it. Another way of doing this is to be closer to the expression we use down here, where we divide it into an amplitude and phase. You take the amplitude of your electric field and you plot it. You take the phase of your electric field and you plot it. Keep in mind that the combined information of the bottom two arrays describes exactly the same electric field like the combined information of the top two arrays. It's the same information, we just look at it differently. And after we do the propagation to the focal plane, we can do exactly the same thing over here, where we have the real and imaginary part of the focal plane electric field and the amplitude and the phase of the focal plane electric field. The specific ways of what these look like, we will also talk about a little bit later. Note how I'm not plotting the intensity. This is something I would be very interested in the focal plane, but here I really wanted to focus on these components. And depending on your application, you will be interested more or less into some of these depictions, some of these properties. So if you're very interested in looking at what are my phase aberrations in the pupil plane and what effect do they have onto my images, then you would specifically focus usually on the phase, on the phase in your pupil plane and then the intensity in your focal plane. If you do wavefront sensing and control, you might actually want to dig into more into specifically the real and imaginary parts. So your application will dictate or will have you choose which of these components you specifically look at. And then again, I just want to write it out explicitly. The connection between the information in this plane to the left and the focal plane to the right is a Fourier transform. This is what we will be using throughout and forever now. I want to come back to one thing, which is I said that we are looking in the far field regime, in the Fraunhofer regime, which means that we have to be far away from an object. This is true. And what is also true that the Fraunhofer integral applies to objects at the focal plane of a converging lens. So what lenses do is they can take an object and put them at infinity, which leads to the fact that we can now treat them with the Fraunhofer integral. And this is why we sometimes also say lenses are Fourier transformers, because they have this property. And so if you just have something very far away, or if you have a lens to put the image very far away, those are optically equivalent. And this is why we can work with this particular framework. Okay, so a brief summary of the first part of the talk is that high contrast imaging systems are optical systems. They can be simple, they can be more complicated, but fundamentally they will consist of pupil planes and focal planes. And the pupil planes and focal planes are Fourier transforms of each other. What I showed you so far, and I'm showing it again on the top left, is a very, very simple optical system that contains one single Fourier transform. What you will see later today in David's talk is, for example, a Leo chronograph and other more complicated optical systems where there are more of these Fourier transforms going on. All right. The next thing I want to talk about is a diffraction, which is the observed effect that we can describe it for optics, and also some of the properties that we keep using when we do optics in high contrast imaging. So the diffraction effect is really what dominates our images when we're diffraction limited, hence the definition. In telescopes, we have to use our aperture because that defines our collecting area. The thing is that imposes an edge, and that is an obstacle for the light. And when light comes to this optical, it bends around those edges, it diffracts. In the case of a very simple circular telescope like here, we have this aperture in the pupil plane, and then when we do the Fourier transform of that, we get this pattern in the focal plane. Now, when you do the math, when you actually take your aperture and you have it as a top hat function and you develop the math, you will see that the Fourier transform of a round aperture is a scaled Bessel function of the first kind. So we call this an airy function, an airy disk, an airy pattern. Airy everything describes the perfect PSF, the perfect image of a round aperture of our telescope. That's important. This is why it's up for a little bit longer. Look at the airy pattern. Just gonna do this. Another way of showing this, which you will also see a lot, is we don't, especially when we look at symmetric PSFs and symmetric images, we don't always have to look at the full image. We can simplify this in plots. And the simplest way of doing this is to just pick one of the axes. You make a cut through, like is done on the bottom right. And you can plot all of the values, and then you get the line plot of this intensity. Also, what I didn't mention immediately, note how I'm actually plotting the logarithm of the intensity, log intensity. This is simply because, especially when we go to high contrast applications, the differences will be so big. And to me, at this point, it is so natural to look at this, but I wanted to really insist on this. If you keep doing your transformations, when you look at intensity, not always, but usually, it is more useful to look at the logarithm of this. So this is exactly the same thing, but blown up again. And what I will flick through now fairly quickly, because you will be doing this in the hands-on sessions, is I showed the diffraction pattern of a circular aperture. But what happens if I don't have a circular aperture? Well, you get a different diffraction pattern. These can be rigorously derived analytically. This was just a rectangle. This is just a hexagon. Then you can start stacking the hexagon. You get something like Keck or JWST, except you don't, because you're missing spiders, you're missing the central obscuration. You can see how this starts adding extra diffraction features in your PSFs. You can do this for all the telescopes. Now keep in mind, we're diffraction limited. There are no aberrations in this, so this is not what it will look like on sky. But in the fundaments we get from optics, this is what it would look like if it were perfect without aberrations. So this would be the VLT. Here we have the ELT. Here we have GMT. And you see that immediately, just by changing your aperture a little bit, your diffraction pattern changes. Okay, one important thing when we talk about apertures and the transformations is that we need to know how the units relate. So the focal plane, the transformation of your aperture is expressed in terms of spatial frequencies. So this means that the physical scales in these two planes are the inverse of each other. When you have something grow in the pupil plane, you will see it shrink in the focal plane, which is exactly why we want to go to larger apertures, because the larger my aperture, the smaller the core of my PSF, which means that I start being able to discern different point sources that are very close to each other, right? So this inverse relationship of the physical scales in these two planes are really, really important. Before I go more into the resolution thing, I want to talk about angles. Now, remember that with the approximation into the far field regime, what we're really interested in are the angles in our pupil plane. So what does this mean? If I look here again at the bottom left, I'm depicting this like simple optical system again. We have the pupil plane, we have the focal plane. At this point, we know that the star is far away. The beams come in as a parallel ray, they hit the lens, they converge into our focal plane. You can see how now I made the choice that the thing I want to look at in my wavefront is the phase in the pupil plane, the phase here, and the intensity in my focal plane, in the plane over here. There is now an off-axis source. So this is not on-axis, it's an off-axis source, like, for example, a planet or a companion star. This comes in at an angle in the pupil plane. It manifests as a tip or a tilt in the pupil plane face, and the focal plane image actually starts shifting. I will go back so you can see the difference. It starts shifting. And then the bigger the angle in your pupil plane, the bigger your tip in your pupil plane, the more your PSF just starts shifting away from on-axis to off-axis. There's many cases in which you would want to notice and use this. One is that when we have fast tip tilt and jitter in our telescope, that's exactly what it looks like. Your PSF starts wiggling around, it starts moving. So when you start integrating, it just smears out. And this is one of the limitations that we're working with. There's different ways around, or at least to limit it. Now, coming back to this idea of angular resolution. So I've shown you now what happens when we have a beam of light come in at an angle. So when you now not have just a single source, but you have two sources, one is on axis, one is off axis, this is what it looks like. A planet that is off axis will be a copy of your PSF, of your point spread function, but at a different point in your focal plane. So this is what I'm showing here on the right. The star is on axis. You can see it's centered in the field of view. And then we have a planet that is just added. Again, the way of looking this in just a line plot is that you expand this. So we have a star, and you can see how the planet, this line, it's exactly the same thing. It's just shifted because of this angle to shift relationship from pupil to focal plane. Now, when we keep talking about angular resolution, the question is, well, how close can this planet actually be to the star so we can observe it as its own point source? And this is where the Rayleigh criterion goes in. Now, the definitions of resolution, there are different ones. Usually in our field, we keep going back to the Rayleigh criterion, which is where if your planet, orange line, is far enough away from your star, the PSF will be so separate that it is not a problem to detect them separately. If it is too close, like I'm showing here on the right, the two point sources will show up as one single source because their sum just manifests as a simple source. And the limit between that is usually quoted as if you have a second source whose first minimum is, this is a bit shifted, so this is still resolved. If the minimum is at the maximum of the original point source, then you can just about resolve them. And obviously, as you increase the diameter of your telescope, then these just start going apart, and this is how we can easier resolve them. So angular resolution, right? We have already heard today that angular resolution, there are ways to go around that. You build bigger telescopes, you make better wavefront sensing and control to actually get to the diffraction limit. The other problem is contrast or intensity ratio or flux ratio. I'll leave the definition of contrast to David. Thank you very much. But in essence, what we're looking at, the ratio of the light that we get from the star, the ratio of the light to the light that we get from the planet. So what I'm plotting here is now a planet that is slightly fainter. It's a factor of 10 fainter. It's far enough away that it's resolved. And we can see how as we start scaling it down, this is now a 10 to the minus 2 planet. It starts sort of disappearing in the wings of the PSF of the star. And so this is just saying the same thing again, where what we really care about is the ratio of the planet light to the starlight at the position of the planet. And this is why also high angular resolution is hard, contrast is hard. What is really hard is high contrast at small angular separations. Because if I put the same 10 to the minus 2 planet just closer to the star, now suddenly it completely disappears. So I promise you, the planet is actually there. You can kind of still see it by eye. I put it in the data. They have exactly the same contrast, but because it is so much closer to the star, suddenly it becomes much, much harder to detect it. So again, the real challenge is high contrast at small angular separations. Contrast is hard, angular separation is hard, but those two together, geez, we probably need HWO for that. And then, I played with a 10 to the minus 2 planet. That's, when you work at these regimes, that's really not that hard. When we look at a 10 to the minus 10 planet, it looks hopeless. Like, how would you, no matter how far away you go from your optical axis with your planet, how do you ever want to see this? Well, the solution here are the starlight suppression techniques. This curve is completely fake. This is not data. This is me just trying to get a point home where at one point, we have to start thinking about, well, if the planet is drowning in the starlight, is there maybe a way how we can shape the starlight so that we sort of dig it away, put it somewhere else in your image? Hence also why sometimes we talk about dark hole digging. We dig into the light of the star to get access to the light of the planet. And then there's a lot of research going on in this part of this very fake plot. About, well, if you have this sort of planet with this sort of flux, how far below or above do you actually have to be about the flux? Wavefront sensing and control comes in here, post-processing comes in here, a temporal evolution of your PSFs comes in here. So this is a really, really hard problem. And it is governed by these fundamental principles, though. Okay, so I've shown you now what the optimal case is. If we can just build the telescopes to exactly the spec that we want, if we can deploy the chronographs, wavefront sensing and control, everything looks great, right? Not quite. Optical aberrations mess it all up. We cannot exist without optical aberrations. They have many different sources. And usually they can... Okay, so here I'm just showing you a perfect wavefront again, just to repeat it. We can see that in a perfect wavefront, the amplitude is just a pupil of our telescope. The phase is 0, which is why the electric field just reduces to our amplitude and we get the perfect PSF. Now, the thing is that in reality, we have aberrations and they can occur both in amplitude and in phase. I mean, aberrations are just a deviation from your perfect wavefront, so they can occur anywhere in your wavefront. In general, we can write this as amplitude aberrations alpha and phase aberrations phi. And in terms of amplitude aberrations, which I will not talk too much about, is they are usually seen as anything that changes your pupil transmission. So anything that either on the telescope directly or inside the masks of your high contrast imaging instrument, you might have an uneven reflectivity on the mirror. You might have dust. You might have unequal reflectivity between segments. If you're on a segmented telescope, you might have a missing segment, like on the ELT. Segments will be taken out all the time for like repolishing and fixing them. So all of these things would manifest themselves as amplitude aberrations. We also have phase aberrations, and phase aberrations have a lot of different sources. In principle, what happens is when you have one of these beautiful plane wavefronts coming in, there's always going to be something, an optic, that can introduce phase aberrations. So when we're on the ground, the most prevalent source of aberrations is actually the atmosphere. So here is where all of the crazy stuff in the atmosphere happens, and that makes our wavefront squiggly. We introduce an optical path difference, which scaled by the wavefront then gives us our phase aberration. What do these look like? How do phase aberrations in the pupil translate to image distortions in our images? What I'm showing here for now is just a pupil plane phase on the left, and again, an intensity in the focal plane on the right. No aberrations. If we do a simple pattern in the phase of the pupil, for example, a sine wave, which we know how to describe analytically, the Fourier transform of that is a pair of speckles in the focal plane, and the distance, so their spatial frequency, depends on the spatial frequency of the cycles per pupil. If I put on a sine with 5 cycles per pupil on the phase of my pupil, the transformation will be a pair of speckles that appear at a distance of 5 lambda over d on each side. If I do this at 10 lambda over d, at 10 cycles per pupil, the speckles are at 10 lambda over d. If I do it at 15 cycles per pupil, they're at 15 lambda over d, and so on and so forth. So this is one way of describing very rigorously what phase aberrations in the pupil do to the image in the focal plane. Now, the thing is that it's going to be rare that we have pure sine waves as aberrations, because that would be very easy to fix. Turns out that we can describe any aberrations as a linear combination of sines. There's other mathematical bases we can use for this, but this Fourier basis or sine wave basis is one that is used a lot. So what I'm showing here is just the sum of all of the sine wave aberrations I've shown before. So the 5, 10, 15, 20 cycles per pupil just added together in the pupil. So they give me the added aberration also in the image. And now I don't have to constrain myself to sines with always the same orientation. I can do this completely arbitrarily, right? We're getting closer and closer to an image that looks like it comes from a real telescope. It's not quite there. It's still too clean. It's still way too clean, mostly because we know exactly the spatial frequency content of these images. But we're getting closer. And this is one of the key components where with aberrations, what really helps us is to break them down in terms of their spatial frequency content. So we can usually divide them into low, mid, and high spatial frequencies. But what you should be seeing here already is that with the aberrations, we're entering the eternal game of high contrast imaging, which is it a planet or is it a speckle? Right? I couldn't tell. I mean, now I can tell because I made the simulation. But if I just look at an image and I look at the speckle, and speckles, PSFs, they're all governed by the same physical sizes, I would not be able to tell whether this is just a speckle that is actually starlight but aberrated, or an incoherent source, a planet, the thing I'm actually interested in. And this is why it becomes so important to look at strategies to actually fix this. Now, a friend of mine and I had some fun last year where in our April Fool's paper, we were like, just run Pac-Man and get rid of all the speckles. Obviously, it's not as easy as that. We wish. By the way, this is real hardware data. We managed to use phase aberrations to actually do this. But it's not as easy as that. And what I'm trying to show is really the need for all of the things we will be talking about this week that Beth already alluded to. Is we need chronography. We need wavefront sensing and control. We need post-processing in order to win this game of sort of the eternal whack-a-mole against the speckles. Before I let you go and I can take some questions, I just want to briefly show some images of low order aberrations. So you might have heard about defocus, astigmatism, coma. And the sources for them are also very, very various. So you can have thermal settling of your telescope, misalignment of optics, fast tip jitter. The important thing is that these aberrations distort the light very close to the optical axis. Remember, the interesting objects are very close to the star. And this is what motivates low-order wavefront sensing and control. So this is also one of these relationships. Low-order aberrations mean close to the star. Kind of sucks if you want to look close to the star. And, mid-spatial frequency aberrations when you go into segmentation. And when you put all of that together, so this is a phase screen that you might see when you observe from the ground. It's still a bit simplified. You get a combination. Here it looks like it could kind of be decomposed into a tip tilt along this axis, but it also has this high spatial frequency content, and then your PSF evolves. And dealing with these PSFs is what we're really trying to do. My very last plot is, well, we can also put this into spatial frequency space. These are low spatial frequencies, these are high spatial frequencies, and look at how much energy we have in each of these spatial frequencies. So anybody doing AO, wavefront sensing and control, you will be looking at power speckle densities a lot in order to figure out how to control your aberrations. And this is it. Again, it was very condensed. I took you through a couple of very important things. I left out some others. We did no derivations at all, which everybody should do at some point. But what I really wanted to just remind before we move on is that we need wave optics to describe diffraction. Diffraction is really dominating us in the absence of aberrations. We can model light as a scalar field, which allows us to use Fourier optics under the approximation of the far field regime. The hard part is to really get high contrast at close-in locations, at small angular separations. And once we add aberrations to the mix, it gets really, 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 really hard. Thank you for all the people who do all the work to try to fix this and to get around it.
Questions? All right, I greatly encourage people to ask questions. I can run a mic to you. Julian can run a mic to you. Okay, Beth's got one. Oh, and there's one in the back. So we'll start with Beth, and then Julian, if you can get the person in the back. Thank you.
All right. So you showed essentially using a sinusoidal basis for the speckle pattern. And then you showed some coma, different aberrations. Can you talk about when you would want to use the sinusoidal basis versus something like Zernike modes and why you would choose between the two?
In what kind of aberration sources are you looking at? If you know that your aberration comes because let's talk about lenses because they're just simpler. If you have lenses that are just misaligned, that introduces low-order aberrations that are clearly defined. So you would just go to a Zernike basis because they completely accurately describe those. Mathematically, you could do a change of basis. But in that case, you would have a combination of different basis modes that make your aberration versus in the Zernike mode, you just have one mode that completely describes your aberration. A Zernike mode is, those are modes on polar coordinates that describe these variations on a circular aperture. I know that's a very abstract definition. Wikipedia has a fantastic image for Zernike modes, but it's a basis. It's a mathematical basis that you can use to construct, in our case, in particular, optical aberrations.
Hi, I'm in the back. Thank you so much for this talk. I'm El Bogat at University of Maryland. I was wondering, since for the mathematical simplifications we're using to make sure that we're at the right distance from the source and whatnot, how much more complicated does it get when you are trying to model issues in your telescope that aren't purely just the optical elements, but potentially internal scattering, stuff like that? When does this scalar approximation kind of break down?
Yeah, excellent question. So I've shown that we actually do several layers of approximations. So the layer before the Fraunhofer approximation is actually the Fresnel approximation. We can use the Fresnel approximation when we want to get out of our standard planes, the pupil planes and the focal planes. One very concrete application of this is when you have two deformable mirrors. In order to control the electric field for active wavefront sensing and control, usually you would put one of those deformable mirrors in a pupil plane because you get full access to the phase that you want to correct. but then you only correct the phase. You also want to correct the amplitude. So the second deformable mirror would be outside of a pupil plane, because due to this phase amplitude mixing, which can be described through the Talbot effect, you get access to almost your full electric field when you try to sense and correct it. Now, obviously, this is now outside of one of the planes that we can access with the Fraunhofer approximation, and this is where we use the Fresnel approximation. Using the Fresnel integral is not that much more computationally intensive than it is more intensive, but it is doable. We do this regularly in our models, but we also know the moment we do a Fresnel propagation, it's like, ooh, this is now gonna increase our computation time. Those are still manageable though. Anything before that gets really hard. Remember that the Huygens-Fresnel principle is not an approximation. Going from Huygens-Fresnel to the Fresnel integral, that takes approximations. Huygens-Fresnel is not an approximation. And I have so far not had to deal with that. That becomes nasty. That is a huge mess. There's like a whole section in the Born and Wolf book that like explains how to do this. There's a lot of things. So Fraunhofer and the one before with Fresnel. Fraunhofer is a subset of the. It falls within the Fresnel approximation. It's just even more stringent. So as long as you're dealing with Fraunhofer and Fresnel, you're fine. Anything before that is really a mess.
Oh, one more. Okay, quickly.
Thanks. So I have another question about the when the scalar field approximation is valid. Does the fact that light from a star isn't perfectly monochromatic, that it's polychromatic and temporally incoherent, make a big difference, or can you usually simulate things as being perfectly monochromatic?
Yeah, so I actually didn't answer one of your questions, which is when does the scalar theory break down? Well, the moment you introduce polarization, for example, that's a vector theory. However, we can still use much of the framework we developed. So this is where it becomes sort of a mix, and you have to be very careful about which approximations you use. So thank you for reminding me about that. Now about polychromatic waves, the approximations do not get rid of the wavelength dependence. There's always a wavelength dependence, and we can develop everything that I showed, we can develop for polychromatic light. So there is an integration of a certain range of wavelengths that we can do. We can then reduce that to do monochromatic waves. When we simulate, what we usually do is when we do monochromatic light, we just constrain ourselves to a very narrow band, which is like one wavelength. And then if we want to do polychromatic light, we do several of those and then we add them up. So we exploit the fact of the integrals in the expressions and we can sum them up. But the approximations do not eliminate the capability of treating polychromatic light and broadband light.
Okay.